Topic 8.4 is looking at what makes a strong acid and base versus a weak acid and base. Just remember, okay, acids produce H plus and bases produce an OH minus when they dissociate in a solution. All right, so that what we have to keep in mind is we're working with solutions. And so these solutions, when you make a solution, is an aqueous solution. And when you have an aqueous solution, you're going to create an equilibrium mixture. So this is where topic 7 comes back into play. So using standard, okay? So if we have HA, because we know that acids have to have that hydrogen that it's willing to donate, and it is in an aqueous solution. And how you know it's in an aqueous solution is there's water present. Who'd have thunk? So now we put our equilibrium arrows to represent an equilibrium mixture. That hydrogen is given off. And so now we have an anion. And then we have H3O plus. So the water has accepted that extra hydrogen. Now we don't have to put that water there in this equation. We could just write HA gives us H plus and A minus, but I want you to be able to recognize both. All right, so the position of equilibrium and where that equilibrium lies actually defines the strength of your acid and or base. So a strong acid, the equilibrium lies extremely to the right, and that means it lies to the products, to the point where we don't actually use an equilibrium arrow and we say there's full dissociation occurring. So HCl is a strong acid. And so with strong acids and strong bases, we just use a forward arrow. And therefore, it's going to release a hydrogen ion and a chlorine ion. All right. So strong acids, strong bases have no equilibrium. Whereas a weak acid, equilibrium lies to the left, to the reactants. And therefore, we have to use the equilibrium arrows. And so acetic acid, CH3COOH, we use the equilibrium arrows because it is weak, and we get H plus aqueous and CH3COO minus aqueous. Now, be sure when you're representing this dissociation, you are representing a negative and a positive, and so just make it a habit of just removing that hydrogen, and don't combine those carbons, don't combine the oxygens, just remove the hydrogen so that the grader can see that you understand what part of the compound is the acidic part. So just write it as leaving off the hydrogen, don't collapse your formulas any tighter. Now, there are very few strong acids and strong bases. There's the majority of acids and bases out there are weak. So we are going to be focusing a lot of time on that equilibrium position to see the strength of the weak acids and bases. So strong acid, that is a good proton donor. And because it's such a good proton donor, it's going to cause full dissociation in an aqueous solution. But when you look at the opposite, it creates a weak conjugate base. And so that Cl minus that we had, if we redraw HCl up here, right? So your base is going to be the one who wants to reaccept the hydrogen if it's a conjugate base. And so that chlorine, and if you look, it is a halogen. Okay, and halogens are very reactive. And so it actually wants to be in its ion form over being in a compound itself. And so that is a very weak conjugate base. So it's not going to readily accept a proton to go back into the HCl form. It would rather stay as an ion form. And we're going to talk about more detail that in topic 9 of why certain ions do that. But at this point, just know if it's a strong acid or strong base, you are going full dissociation and the conjugates are weak. Whereas in a weak acid, they're poor proton donors. And so you only get partial dissociation. But because you get that partial dissociation, because the original acid is a poor donor, That means its conjugate base is going to be strong, which means it readily accepts the hydrogen ion, which again pushes the equilibrium back to the reactant side. So strength is the measure of dissociation in solution. How many protons are readily available in that solution will then give you details about the strength of that acid, which then can be measured with your titration method. Strong base, very similar, right? So equilibrium lies extremely to the right. And so we have sodium hydroxide, it's going to be full dissociation into the sodium ions and hydroxide ions. And then if we have a weak base, like ammonia, and ammonia is just so much easier to see reacted with water, so we always put it with water. And that is going to give us NH4+, because you'd be like, where did that other hydrogen come from to get NH4+? Yeah. And then you get OH-. So here are two examples of a strong base and a weak base. As you can see, there is that characteristic OH that signifies a base. And that OH could either be in the alkali, as we talked about in 8.2, where the hydroxide is in the base itself. Now, more times than not, the hydroxide in the base itself makes it a strong base. So sodium hydroxide, lithium hydroxide, potassium hydroxide, because they have the hydroxide present, they are a much stronger base. Whereas bases that do not have that hydroxide and they only become or release that hydroxide when they're in an aqueous solution with water, that is why it's much weaker, because it has to pull that hydroxide from the water molecule itself and not from itself. So just like in acids, a strong base is a good proton acceptor, because in a Bronsted-Lowry acid donates, base accepts. Okay, so because it's such a good proton acceptor, it causes full dissociation. Therefore, it creates a weak conjugate acid, which will not readily donate that proton. A weak base, I wrote acid, a weak base is a poor proton acceptor, which causes partial dissociation, which creates a strong conjugate acid. I'm doing good here. Which will readily donate a proton back to go back into that weak base. So same thing, that explains why we can use a forward-only arrow for a strong base, because it goes to full dissociation, whereas a weak base, because it has such a strong conjugate, it pushes it back towards the towards the left with reactants. Strong acids and bases. Yep, going to tell you, you got to memorize these, okay? So strong acids, we have HCl, hydrochloric acid, H2SO4, sulfuric acid, and HNO3, nitric acid. Bases, we have lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. You just got to memorize them. I'm sorry, that's just the way it is. Everything else is weak, okay? And you do have a list of weak acids and bases in your data booklet in section 21 for organic acids and bases. But if it's not one of these 7, it is a weak. And so that's why we spend so much more time looking at the equilibrium of a weak versus the strong dissociation of a strong acid or base. But just some examples, common ones that are used all the time. Acetic acid, carbonic acid, phosphoric acid, and then you have your organic acids. Like DNA, deoxyribonucleic acid, amino acid, so on and so forth. So there's hundreds of organic acids out there, which is why you have section 21 in your data booklet. Some weak bases, most common, NH3. You see that one all the time. And then you can have an organic derivative of NH3, like C2H5NH2. And so that's just taking that ammonia and adding it as a amine onto a carbon group, which again, you can do so many different forms of that type of weak base. Then what can we do to test for strong and weak if you're given an unknown solution? Well, strong acid and bases contain a higher ion concentration than weak. So use that to determine or to distinguish them. This is only valid if you have the same concentration of acid and base and at the same temperature, because pH is temperature dependent. So because they're ions, you can look at electrical conductivity. The more ions you have present, the more conductivity you can have, and you can use a conductivity probe to determine that. So a weak acid or base has low number of ions, therefore low conductivity, so on and so forth. You can look at the rate of the reaction, which strong's going to have an increased rate of reaction because it goes towards full dissociation. This is really important to understand for lab safety and what kind of acid or base you're working with, so you know what kind of safety precautions you need to take. But rates of reactions is not good for quantitative. It's only good for qualitative observations, but it is still there. And of course, pH, right? Because pH is a direct measure of hydrogen and ions concentrations. And even though we can only test pH with a pH probe, if you know your hydrogen concentration, you can go out and figure your pOH from your hydroxide ion concentration, because we know Kw equals hydrogen ion plus hydroxide ion. So since we have this equation, even if we're working with a base, you can still figure out that hydroxide ion concentration. And that's going to actually give you a direct comparison of strength based off your concentration values. But remember, hydrogen ion concentration is not the same thing as the concentration of the solution you made, because you could have a 1 molar solution of HCl and CH3COOH, but they're not going to have the same number of hydrogen ion concentrations because they dissociate differently.